Hello, everyone. My name is Sydney Gable, and I'm a graduate student in the Department of Earth and Environmental Science at the University of Michigan, studying seismology. Unfortunately, I'm not able to be with you all today, but for the next few minutes, I will be giving you a short introduction to earthquakes and seismic waves. Seismic waves are simply defined as vibrations that travel through or along the surface of the Earth during an earthquake. Earthquakes are commonly caused when friction causes a buildup of stress at the boundary between two pieces of shifting rock. We call this a fault, and you can see an example of the San Andreas fault in the picture in the middle. When the rocks are no longer strong enough to hold this immense amount of stress, all of the energy is suddenly released in the form of seismic waves. These vibrational waves are what cause the shaking that we feel during an earthquake. On Earth's surface, there are large chunks of the crust and upper part of the mantle, which are called tectonic plates. These plates move very slowly relative to one another and can create earthquakes as friction builds up between them and then is suddenly released. You can see in this figure the blue lines that indicate the boundaries between tectonic plates and the red dots, which indicate the locations of the largest earthquakes that occur on Earth. They generally correlate really well with one another. These large earthquakes often occur at subduction zones where plates are pushing against each other and one plate moves below another, such as in southern Alaska and Japan, or they can occur at transform faults where the plates slide past each other sideways, like the San Andreas fault in California, which you saw in the previous slide. We can see from this map that Michigan is nowhere near any of these tectonic boundaries. Therefore, we don't have very many earthquakes, although there are some small ones on rare occasions, which you'll learn about later. Some earthquakes are large enough to be felt, but the vast majority of them are so small that we need instruments called seismometers to detect and record them. The very first ancient seismometers looked like this one on the left. There would have been small metal balls placed in the mouths of the dragons at the top, and during an earthquake, the balls would fall down into the mouths of the frogs at the bottom. As time goes on, we have moved to a bit more sophisticated methods for measuring earthquakes. In the center, we can see the schematics for a seismometer that draws waveforms on paper using a simple spring and weight system that moves the pen up and down. Today, we use the same idea, but we have upgraded our instruments so that they are able to use electrical signals to record data digitally. Since seismometers record any type of vibrations and not just earthquakes, we need to be sure about what we're measuring. When we look at the data, there are a few characteristics that we look for to determine if our signal is in fact an earthquake. Specifically, we look for the arrivals of different kinds of seismic waves. The first type of seismic wave that will arrive at a sensor is the P wave. This is a compression wave that causes expansion and contraction and moves through the Earth in a very similar way as sound waves move through the air. The second type of wave to arrive at the sensor is an S wave. This wave moves particles in an up and down shearing motion, similar to how a guitar string moves when you pluck it. Unlike P waves, S waves can only move through solid materials. Finally, we can observe the arrival of surface waves, which are the most destructive parts of an earthquake due to their type of movement. These waves move only along the surface of the Earth and are made up of two types: love waves, which move the ground in a zigzag pattern, similar to the way that a snake moves, and Rayleigh waves, which move the ground in a sort of backward circular pattern, which is very similar to how waves move in water. In this final animation, we can put all these pieces together to see the progression of an earthquake and how the waves move through the Earth and across its surface. We can also view how the signal would show up on a seismometer that's recording the earthquake. I'll play it again for you to see one more time. Thank you for listening to this short introduction to seismic waves and earthquakes, and I hope you enjoy the rest of the presentation.